4, okay, 4 demos. That's good. Look forward to it. Let's see, what else? Project 3 will be due very soon, right? So are there any questions about Project 3? I mean, we talked about it last time a little bit, so I'm sure that you have some questions. Good.
Is it all right if we use the CGAL libraries, half-edge, and polyhedron data structures?
Yes, you can. That's fine with me. If you use data structures defined properly and working, the structures, maybe even the operations on them to insert, to delete, to modify, it's fine with me to do that. So point it out to me when you actually do that yourselves. Okay? So when someone actually takes on this major pain of developing a half-F data structure like creature, that is a major issue, very complicated, requires a lot of thinking and effort and debugging, let me know. Okay, but in principle, yes, for this assignment you can use public domain software for that and data structures. So how do you create this hierarchy? You're already having fun with the third project. I see you smile, so you're already enjoying it, right? You have not started yet. Oh my goodness, the third project is a big one again. The first one was really hard. The second one was easy. The third one is again a little bit harder. And the last one is, well, as hard as you make it, right? So is everything clear? Let me talk about the hierarchy, okay? A hierarchy of Voronoi diagrams. So again, the way I use this third project is I'm not really telling you how to do every single aspect or step of that assignment. There's a lot of freedom for you to take advantage of. And so what I'm seeing is that you have an initial original scattered data set of, well, some size, 1,000 points, 10,000 points, 100,000 points. And then the ideal would be the following. The ideal would be that you construct a Voronoi diagram consisting of 5 points that are the best possible 5 points one could possibly choose from the data set to construct the coarsest Simpson approximation, right, for the entire data set. So, of course, that is a combinatorial thing. You have that, I mean, choose the best possible 5 from the number of data sets, data points you're given. So, right, 10,000 choose 5 is a big number already because there's a combinatorial explosion because of the factorial in there, right? So you have to think about it. If you really want to go in that direction and you want to think about it that way, start with a coarse Voronoi diagram consisting just of 5 points, the best 5 points you can choose, right? Ideally, you have to do an exhaustive search, picking all point subsets consisting of 5 points from the given points. That's the idea. So then you go to the next question, okay? Next level would be the best possible Voronoi diagram and the Simpson interpolation living on top of it that consists of 100 points. Then the one that consists of 1,000 points, right? So it's always the given number of sites and choose so and so many from that. And then you have the combinatorial problem. You can tackle that if you want to. So if you really go into that and try to get the best possible or get close to the best possible, a best possible representation consisting of 10 points, 100 points, 1,000 points, do that. It's very interesting to think about that. Then in terms of the hierarchy construction, I think you want to do that in a restrictive way. In a restrictive way, in what sense? Restrictive in what sense? So say the first approximation you construct is based on 10 data points, 10 sites, and those you keep fixed. Those are the ones that you keep. Okay? So when you go from a 10-point diagram, a 10-point Simpson approximation, to the one that consists of 100 points, you keep the original 10 that you have selected in there. Okay? So going from 10 to 100, you would keep the 10 you have already there, and then you add 90 additional ones. Okay? So you will be restrictive in that sense. You always add, right? So going from 10 to 100, you add 90 to the originally chosen 10. Going from 100 to 1,000, you keep the 100 you already have, and you add 900. Okay? So build the hierarchy in that way. So no matter what, in the end, you will, of course, pick all the points, right? The limit is, well, you use a Simpson interpolation that considers all the sites, all the function values that you have. And the Simpson interpolant over all the sites is the ground truth, call it that, And so that's what you want to converge towards, right, by having the coarser resolutions. So when you show to me a bunch of snapshots, right, a sequence of image 1, image 2, image 3, image 4, and image 10, I would like to see progressively refined Voronoi diagrams. You show me the structure, this beautiful underlying tessellation, right? It's a 2D picture, all the edges, and you show it to me. Tessellation 1, tessellation 2, tessellation 10. And just looking at that, one will see where the structure got refined, because there was a high error of approximation in those regions where we see refinement. And then in addition to showing these finer and finer tessellations, also show me then the function defined over that tessellation, right? And I would like to see it in two ways. I mean, one is just to use Gouraud shading in that plane, right? And the other way to show it is as a surface above the plane, right? Triangulated surface, which you should flat shade. So, triangulated surface with the triangles having a constant color based on their normal. Okay. So that's that. It's all clear? It's all clear? Do you see that in the back of your mind what the program should be doing? Now, if you want to be clever and do certain things in parallel of multiple threads running, doing independent things that are indeed independent in terms of refining the Voronoi diagram, then do that. Inserting points or inserting sites into a Voronoi diagram, is it a local operation or is it a global operation? Does it have a local effect only, or does it have a global effect on the entire diagram, the entire tessellation?
It has an effect on the cell that point lands in and its neighboring cells, but cells that are far away won't get affected.
Okay. Is that true? Inserting a point in a diagram will only affect some tiles, but never all. Sometimes in a local neighborhood where the insertion takes place, but it will never affect all of them.
Well,
That's
if
true.
there's like 4 tiles, then it might affect all of them. But
Okay.
if there's like 1,000 tiles, then
You think it's local then? If there's multiple layers and layers of these pentagons, heptagons, hexagons, octagons, whatever I insert here, you think only the local tiles get affected, never the ones very far away. That's your intuition, right?
yeah.
Is your intuition right? Is this intuition right? It seems reasonable, right? I'm thinking, is he right? I have to construct only one counterexample in my head. Can we do that? We can all have our brains thinking about the counterexample. I mean, brains times 20. We have 20 brains here, right? So think of the counterexample. Come on, 20 brains together must find a counterexample.
You could have like a degenerative case where you have like a big circle of Voronoi points, and then if you insert in the middle, that can affect.
Yes. Yeah. So depending on the arrangement, the point arrangement, you can indeed have situations where the insertion of one point causes a change of all the tiles that already are there. Whether it's 1,000 tiles that are there or a billion tiles. Why? The ugly counterexample is this one, right? It's not fair to think of that, because, but if I have all points, this is my point set. What is the Voronoi diagram for that? Well, the Voronoi diagram for that are these infinite tiles, right? Okay. Think about what happens if I insert a point. That is not on that line. Okay. There are other arrangements that are nasty. So, all right. So there will be issues, right? If you think that you can use a parallel paradigm to do certain operations on these nice tessellations without having an overlapping stencil that gets affected, then well, you have to think about that carefully, what that means. And under what circumstances you actually can have multiple threads operating on which chunks of that when it comes to the operation of insertion, okay, as a condition. Anyway, so what you will need to do, you need to do refinement. I should talk about this so you have a little bit of an idea what principle to consider, not what specific method, but what principle. Refinement of the VD, the Voronoi diagram. So say initially you have this type of tessellation. I can only draw this beautiful one, other ones are too hard. Okay, and there are some more around it. And so then, okay, these are the sites that are currently the chosen ones to define the diagram, to define the Simpson interpolation that lives above the diagram. Now here comes the step of refinement or hierarchy or next level. How do you refine this? Where should you refine it? There's more points, right? There's a gazillion points which you have not considered yet, but there's a gazillion sites everywhere. They are just not considered to come up with a tessellation at this point. So refinement means, well, you pick a few more of these currently unused sites. Which ones do you pick?
The ones where you found that the error was highest.
Right. That's one way of doing it. Ideally, you could pick also another one. Your strategy could also say, pick the one that reduces the error maximally after insertion. Maybe, if I pick this site or a few sites that are in the tile that have the largest error, that will be indeed the effect, that those chosen when inserted lead to a new approximation that has the greatest reduction in error possible. That's an interesting question. Okay? No matter what, you can have a tile here, call this tile I. This is one of the original sites, xi. And so you have, say, k additional site values in this tile that are currently not considered. The value, the function value at this center point, fi, that is being interpolated precisely, exactly, because it's construction itself. The construction makes sure that the Simpson interpolant goes through the 6 function values at the size, but not through the ones here. So you could say there are k additional unused original tiles, original sites inside or an edge inside tile I. Therefore, you can compute an error just for that tile, right? So you could say, well, if there are k, you could compute an error for this tile. Error of tile I is just, if you use the root mean square error, would be, see, root mean square error is a good one to choose, I tell you that. Root mean 1 over k square, summing all the differences from 1 to k of the differences between Simpson at, call these j's, okay, j from 1 to k, Simpson at these points, xj in there, minus the function value fj at those sites in there, squared. Okay, so you could call this is error I, right? The error for tile I. So then you will have an error for tile I in EI. You will have an error for this tile, maybe error K. You will have an error here, error L, error M, and so forth. So you have all these errors for the tiles And then you could introduce an order. You could order the tiles based on error, right? Again, this is a hint that I want to give you. Because an insertion in general, an insertion in one tile will indeed have a limited local effect only, in general, okay, in general. So when you refine in this area, the other tiles do not change, and therefore also the errors do not change. So you want to keep these in a list. Ideally, you want to have a linked list or an ordered list or an ordered array of all the tiles based on their errors. And the tiles that are the worst in terms of error behavior should be at the top, right, of your stack. At the top should be the tiles with bad behavior, with large errors. So you can always grab them from the top of the stack and use them for refinement. And then, of course, after refinement, if I choose some point in this area, if I refine, put this one in there, choose this, then I have a new configuration, and the local neighborhood is affected, then I get more tiles, and I have to properly insert these new tiles, updated tiles, into the ordered list of all the tiles, right? Because after refinement, they should go further down in the stack of tiles. They have improved. They are better. They have a smaller error, right? So that's another trick in order to always, keep an order, right? Keep the ordered list and only insert into an ordered list of error-specific tile order. Okay. So good principle would be, you always keep an updated, ordered list of tiles based on their error. Okay. And then you always pick the one, or a few, you pick the one in general, pick the one with the largest error and refine it by doing exactly as Kate said. You pick a few points in it, not necessarily just one, but a few. How many? Think about that. Should you use just 1, 2, 3? What is a good number? It's for experimentation, right? Pick tile with largest error, and insert more sites there. Okay, there. Question is, could you parallelize this approach, and could you in parallel update multiple tiles, inserting points in tiles which are indeed neighbors that are close to each other, and do the update operation in such a way that you can take advantage and get an acceleration by doing it in parallel. Because if you do it in parallel, there's algorithmically and software-wise it becomes more complicated, but if you have multiple threads running, maybe you can win it back. Okay, so think about that. If you want to do that, some of you guys into parallel programming, think about that. Parallel updates. So always take the 5 tiles or the 10 tiles with the respective largest errors and refine them all in one step in parallel, right? So, okay, what I mean in terms of a hierarchy. So all these tiles get refined, and smaller tiles will emerge until it looks like a crystal structure, right? A grain structure. When you cut a crystallized material, you would all see all these grain boundaries, and they look like that. It gets finer and finer. Okay? Sounds good? Sounds good. Now, many of you have heard about subdivision schemes, right? Curve subdivision, surface subdivision, volume subdivision, subdivision surfaces, subdivision solids, refinement, not insertion, B-splines, something like that, right? All of that stuff is related, of course. And interestingly enough, there's also a relationship of a particular type of subdivision schemes to an operation that I will talk about after I talk a specific type of subdivision, namely Do-Sabin subdivision. Who remembers what Do-Sabin subdivision is? Who took that? Who knows what that is? You've heard about that, Jennifer? No? You've not? Okay. Have you heard about corner cutting algorithms? Corner cutting? You've heard of corner cutting.
It was for triangulating an arbitrary polygon corners off to isolate it.
Corner cutting is really, think of carpentry, okay? You have a cube, and then you have a saw, and you cut the corners away. And then you also cut the sharp edges away. Okay, so initially, this is a simple example that you can still figure in the back of your brain. Take a cube, a wooden cube, and then you have a saw, and you saw all the corners, right? You saw them away, cut them away. Corner cutting, corner cutting. So you have 8 corners, so the corners, instead of remaining a vertex, become a triangle, a flat triangle, right? When I cut the corner away, the vertex goes away and gets replaced by, well, a triangle with 3 no vertices. The corner cutting also means I actually smooth or cut along the edge. So I will also cut diagonally in the edge area, so the edge goes away and becomes a quadrilateral. So I combine this in one step, and this step then leads to what is called Do-Sabin subdivision scheme. These subdivision schemes are extremely important. They were developed to a large degree by one of our friends here at UC Davis. His name is Tony DeRose. Have you heard of his name? Tony DeRose? Tony DeRose, have you heard his name? Yes. Tony DeRose is the vice president for research at Pixar, and he studied at Davis. So he studied physics at Davis, not computer science. Anyway, he's a very nice and clever and accomplished gentleman. So he studied physics. Later on, he studied computer science at Berkeley. Then he became a professor, assistant professor, associate professor, full professor at the University of Washington, a great place, right? Also for graphics. And then decided, oh, okay, this isn't it. I go to Pixar, make movies. Okay, so he used the stuff that he had worked on as a focus area for large number of years, namely subdivision surfaces, to model characters. Have you seen the movie from Pixar? It's a short one, an award-winning short movie where it's an old gentleman playing chess with himself, and he has no partner to play with, so he switches sides and plays against himself, and is angry when he loses playing against himself. Okay, so you see this very intricate detail and geometry. That is subdivision. Those are subdivision surfaces. Subdivision surfaces are now used to model pretty much all the characters, the surface geometry that you see in these Pixar Disney movies. So it's quite a big impact. It all goes back to this very primitive or simple idea or genius idea of just cutting the corners, right? Cut this corner and then trim this edge and then cut this corner and repeat this, iterate the process. When you iterate this process of cutting the corners, 1 time, 2 times, 3 times, ultimately some of these schemes will converge towards something that is smooth. Okay? So if you start with a cube and you cut all these corners, boom, 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 first time, second time, third time, ultimately it will look more and more like a sphere. So I just want to get, your appetite started on this a little bit. This is just for fun, the Do-Sabin. And the Sabin guy is again Malcolm Sabin. Do-Sabin subdivision. This word subdivision has many, many synonyms actually as well. Subdivision is good. Subdivision. So it's also called corner cutting. It's a corner cutting plus edge cutting. So how does this work? An example. Take a cube. Cube transform to a sphere. Will it really be a sphere? In the case of this particular scheme, will it converge to a sphere? Yes or no? You can think about that. So I have a happy cube. And now Do-Sabin does the following. Do-Sabin takes every face of a polygonal mesh. It can be an arbitrary polygonal mesh. Okay, it doesn't have to be just four-sided things. It can be a mesh of three triangles, quadrilaterals, and pentagons, hexagons, heptagons, octagons, etc. It takes the center, defined as the centroid of the vertices defining each polygon. Okay, so it takes the center of each face, and I only draw these centers on the visible faces, the front faces, the top, the front, and the right face here. Then connects this centroid of the faces to the respective vertices defining that polygon. Okay, so it connects, or does not really connect, but mathematically that's what it does, connects the centroid to the vertices of the surrounding polygon, and then takes the midpoints, takes all the midpoints of these new edges, and you get new edges, namely these guys, the midpoints here, this one, and this one. Okay, again the same construction on the front face. You take this vertex in the middle, this new helper vertex, have the edges to the surrounding vertices and take the midpoints of these edges. So you will get, when you look at this stencil of edges and take the midpoints, you will get these guys. Again, on the right face, you do the same thing. You take the centroid, think about connecting it to the surrounding vertices, and take the midpoints of this spider net that you get. Get one here, get one here, get one here, and you get one here. Okay, and this is it. This set of vertices, the bullets, is the next generation of vertices generated from the parent set, namely the circles. Okay, so these were the originals. And then these guys are the results of performing the first step of Do-Sabin subdivision scheme. So I call the originals level 0. And then this is level 1. Okay, so these vertices will also be connected in a particular way to define a new closed triangulated surface. Well, the top ones still define a flat surface, this square, which is a smaller version of the original polygon on the top. The one in the front is also just a reduced version, shrunk, of the original front face. The same on the other faces. So the 6 faces of the cube all have become smaller faces, and now I have cut the corner away, right? This is a corner cutting. With my saw, I cut the corner. That means I introduce a triangle there, right? So in the triangle, you see where the triangle is. This is that triangle. Okay. So now these are these new things that I've created by cutting the corner. This guy, and this guy. Okay. And this happens at all the corners. So just this part of the new mesh would be this. And I will not draw more, otherwise it gets too confusing. But I think you get the idea, right? What happens essentially, and this also happens, of course, on the other side. Okay, is it visible what I mean? Huh? So you have a nice big fat cube to begin with. Then you cut all the corners. Boom. This one and the 7 others, and you also cut the edges. Boom. Right? And then, well, the number of polygons increases. The topology changes. Certain types of polygons always remain the same. They just will get smaller and smaller, namely the original ones. Okay? Now you iterate this. Okay, this was level 1. Level 2 will operate according to the same principle. Level 2, well, I mean, first you have to insert these new polygons, these quadrilaterals here along the edges, and these triangles You have to insert them in the structure, right? And then you iterate that. Then you go from level 1 to level 2 by, well, taking these child polygons and making them smaller again, by again applying the cutting mechanism, right? And the cutting in the Do-Sabin is take centroid, connect to vertex, take midpoint of connecting edge, and connect in a way, right? That's it. So take a look at this, read the paper, find it, the original paper. Read paper. Obviously, this must be a good method, an influential method, otherwise it wouldn't be named after someone, right? So, okay. Again, the intricate part of this is this was the centroid, right? C is the centroid of a face. And what you do is you connect these centroids of all the faces to their surrounding vertices, and you split this resulting dotted edge at the midpoint. That makes the Do-Sabin subdivision, okay? It uses a ratio of 1/2 to 1/2, okay? So this ratio characterizes this particular subdivision mask, okay? So there's the other issue of a subdivision mask. The subdivision mask tells you how to take a particular polygon and how to replace it by a new one, okay? And there's different ways to do that by doing certain combinations of the surrounding vertices that define that face, okay? So Do-Sabin is a very specific one. So this ratio 1/2, 1/2 defines this mask, how to take an original polygon, replace it by something new. So you can immediately see that you could use a different ratio there, right? You don't have to cut there at the midpoint, but you can do this with all kinds of ratios, right? Cut much closer to the original edge, right? Just make much smaller triangles initially. Make this triangle, right? And out in the limit, you can also use big ratios to make these triangles extremely big. What do you get if you make these triangles and then you get an octahedron, right? And so this is fun stuff. Okay, you should read about it. Now, there's an interesting relationship. This was just a note. An interesting relationship between this and Voronoi diagrams. So there was this principle of duality, right? Duality. And in this context, the two dual structures that we talk about is the Voronoi complex, the Vor complex, and its dual, the Delaunay or Delaunay complex. It turns out that by invoking a method or a principle like this, shrinking things, cutting things away, you can have a transformation, a beautiful geometrical transformation from this complex to the other, and vice versa. Okay. One can define a continuous I call it morphing operation, transformation, morphing operation that transforms the Voronoi complex VC, this guy, not venture capitalist, but just Voronoi complex, VC to a DC. Okay, and I'll show this first, how to do this for the 1D case, 1D example. if I have a 1D example, and here are my sides, side, 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 and side. Okay. So those are my sides. The Voronoi diagram is defined by the hyperplanes being the perpendicular bisectors, i.e. the midpoints of these intervals, right? So these perpendicular bisectors are just the midpoints between two circles. So, okay. So I want to copy this down. This will be the continuous morph. Top. Top, top. Okay. Top, top, top. I don't even worry about numbering the circles. It's irrelevant. These are the sides, and so the Voronoi diagram. Well, the Voronoi diagram is defined by these midpoints, right? Always halfway, but I want to carry them through the entire hierarchy here. So these are my midpoints. Okay. At my sides, I have function values, right? So I have function values, f. This is the f direction. And here, this will be my transformation. Transform. So if my initial value here is maybe this height value, here the function value living here is this height, here it is low again, and here it is higher again. Okay. So the Simpson interpolant itself could define, well, a piecewise constant function, right? Over each tile I have a constant function value. It's natural neighbor interpolation, right? I mean, if I'm closest to this particular site, I inherit that person's or that site's value, right? This nearest neighbor interpolation, right? Need a function value here. Tell me which my closest point is, and I take that value as my function value. Okay, so all the things in this tile, in this tile, in this tile, those values are inherited by their respective tile they lie in. So, right, this is a piecewise, this is the way I begin, a piecewise constant, piecewise constant, piecewise constant, constant approximation, app for approximation. And this is induced by the tiles themselves. First tile, first value over the entire tile. Discontinuous jump, second tile, second value, well, second tile value. Okay, third tile, third value, and last tile, last value. Okay, so this is a piecewise constant function. It jumps up and jumps down. Okay, this is discontinuous, right? Obviously. Discontinuous. And now I shrink the tiles. I shrink the tiles, say, down to half their original size. Shrinking something down to half the original size is done here. Okay? In a sense, you can think of this operation that was applied to the top face as the shrink operation of factor 1/2. Okay? Meaning I take center point, vertex, take the new midpoint. Okay? Call that shrinking by 1/2. Not really in terms of area, but in terms of taking the midpoint of the edge. Okay? So if I shrink these tiles also in the corresponding value, I would take this tile and shrink it to, well, this new one. Take these two midpoints. I take this tile and shrink it to, well, this one. Take this midpoint and take that midpoint. Okay? And that's what I put on the next level. I shrink it. Now I shrink this tile now to half its size. It still goes to infinity to the left, but here I take this midpoint. Okay, so this will be the new endpoint of a tile. So I take these two midpoints, this guy and this guy, and here I take these two midpoints. One midpoint lies here, and the other midpoint is this guy, and I take this midpoint. Okay. Now the tiles, the original tile size was this. The original tile was this. This was the original tile configuration. Now I have shrunk them down to just half their volume, half their area, half their width. So now the tile ends here. This one just begins here, goes like there, goes there, and here the tile is here, and this tile is like that. Okay, I still have the function values over the original sites, namely this guy and namely this guy. This value and this value. Okay, so now I have, again, I associate the same function value over the tiles, but the tiles are now smaller. The tiles now end here. And this tile is only valid for this span. This tile is only valid for this, and this tile goes from here to plus infinity. Okay, so my tiles have shrunk. So what to do now in between? Now it's even worse than discontinuous. It is piecewise constant, but in certain regions it's not defined at all, right, the way I've drawn it. So it's worse than discontinuous. So what to do in between? You use a ramp, right? Just connect it. It's by a line. Okay, so we just connect this now by lines, by linear functions, blending functions. Okay. You will see that this will converge to when I do this in the limit, right? Okay. Okay, this was shrinking the tiles down to 50%. Into the limit, I shrink them to size 0. Okay. So the last one I will draw is I shrink these tiles to size 0. What will that mean? I make these plateaus become of width 0. Okay. And these ramps going up, going down in a linear fashion are the only ones that will be left. Okay? So at the end, I have, when I shrink this to 0 now the tile, I just indicate this by this bold-faced little chalk here, the tile is now just the point itself. Otherwise, there is no width to it. So I still have the value here. Same value here, I have the same value. Always the same value at the original sites. But now, the tiles associated with these guys have gone to 0. Therefore, if I expand these linear ramps now, I have pulled them even further, namely connecting the sticks. Okay? So now I get this representation. Okay. You see the continuous operation there, that I can do this with a slider on the side. Huh? And the slider would merely shrink or open up those intervals. Yes, you see?
It just seems like a modified Euler method discussed in the first few weeks of class, where we're taking half from the left to the right. Well, eventually we went to the gradient.
I've never thought about the relationship between these things and finite difference schemes, but maybe there is a relationship. I cannot comment on it right away, but think in these ways. So, from a discontinuous function to a continuous function, right? From a piecewise constant to a piecewise linear approximation. Well, it interpolates at the original sites, and in between it approximates, right? So, and which is continuous. Huh? So this is piecewise. We have morphed it or transformed it to something that is piecewise linear approximation. Okay, and this was discontinuous. Now it is continuous at least. Okay, C0 continuous. You see that you can have a slider here from 0 to 1, right? Call this configuration 1, call this 0.5, and call this 0, right? And then that value, moving up or moving down, could change between this behavior as one extreme and this behavior as the other extreme. This is also beautiful because it changes the order of continuity and the order of approximation, right? From plateaus everywhere to linear functions everywhere. You can even think about, can I iterate this process, and can I get even smoother and smoother? Looking or approximating pieces, functions. Well, here, it's a different world. I worry about smoother and smoother approximations of spheres, right, say. start with a cube, cut the corners, and iterate this process, and it gets smoother and smoother. It still always remains polygonal and flat-faced. Okay, it will always be flat faces. What happens here? Can you iterate this process even further? Think about that. Now we can do this. This was just the motivation from the 1D case. If I can do that for the 1D case, I can also do this for the 2D case and the 3D case. Yes, Jennifer?
For the 1D case, what's the purpose of the intermediate step, since in the end it just looks like you connect all the points with lines?
What is so intricate about it? The intricate way to think about it is also in this context, when we come to surfaces and volumes, that you can have a slider on the side which can continually apply different masks for refinement and subdivision. Okay, you can control that, going more smoothly from the cube to the octahedron, and in between getting all these other polyhedral meshes. Okay, by just one slider on the side, you can get a multitude of shapes. Either the shape that is the original cube or very close to it, to, well, in the limit, an octahedron defined by the 8 triangles. Okay, and then by having a slider, you can morph this. In the 1D case, it's just to motivate how that works. Okay, 2D case, 3D case is really where you see that it might be useful for something. Okay. All right, 2D case, 2D setting. 2D setting. So the important thing is to worry about this operation. The essential operation is how to shrink and replace a tile, right, in a Voronoi diagram. Here, this was the operation how to replace a face of an arbitrary mesh of some surface, some geometry, right, some body, some object. And now we talk about this one, or this particular subdivision, in the context of a planar tessellation. Apply Do-Sabin subdivision scheme to a VD, a Voronoi diagram. Okay, so how do I do that? I start with my beautiful, simple example of nicely arranged points. Some of the things I talk about are just beautiful tricks that we like to play in computational geometry. It's just inherently beautiful, okay? So the original Voronoi diagram for these sides looks like this. Should draw this rather precisely now, okay? We need the atomic shrink operation for a polygon in the plane, right? For this three-dimensional setting, this is really the three-dimensional setting, of course, right? X by Z. You have some polygonal mesh of something that lives in 3D. Now our polygons actually are the polygons in the plane. They are flat, and we need to worry about the atomic operation. The atomic operation whether you look at these not necessarily flat polygons and the flat polygons over there, it's always this. You have some kind of polygonal creature. Okay, you compute the centroid, summing the coordinates up of the, in this case, 5 vertices, and divide by the number, and you get the center. Then you connect this new the centroid with the original vertices. And if you use the subdivision mask of 1/2 to 1/2, or 50%, 50%, then the new vertices that will replace the original vertices now drawn as circles, will be, well, the bullets. They are living halfway from the centroid to the surrounding original points, and you get a new miniature version, smaller version, a copy of the original polygons, just smaller. So we do the same thing there, right? So this polygon, again, in this context is not necessarily flat, but here they are flat. So if we do this here, we use a 1/2 to 1/2 mask for subdivision. Then I will not even draw these connecting edges from the centroids or the sides, right? The centroids over there get replaced by this original sides here, okay? We don't compute centroids. These are the centers of the tiles. Those are the ones we use. And we connect our sides to the surrounding Voronoi vertices. That's what we do here. Take the side, connect it to the Voronoi vertices, and take the midpoints of all these connectors to come up with a new tessellation. Okay? So I will just draw right away the new vertices. So what happens, the atomic operation, if I just focus on one of these hexagons? This is one, and this gets replaced, right, in one step by a miniature version of it. Gets replaced by it gets replaced by 6 points first, right, here. Okay, defining the smaller version of the original tile. But then I've pulled this away from the neighbor tiles. There's a gap now. There's a hole. This hole is not allowed. So I have to also worry about establishing new connections to the neighborhood. Okay? So this operation also forces these types of new connections. Okay? And this explains fully what happens in a local neighborhood. All right. So what do? I give you the resulting new children tiles of this operation first. Okay, see that, how that works? Smaller versions, just miniature versions, miniature copies of the original guys. And so forth. And now, what has effectively happened? The edges have a dual use, right? Every edge is a double edge in a sense because it's a shared edge, right? The edge belongs to the right neighbor and the left neighbor. And what I'm doing by this operation, I'm actually taking these two edges, it's a double edge, and pull them away from each other. That's what this operation does. So your data structure to do this already should represent this edge as a twofold edge, which has two uses, namely the left use and the right use. So if you use the good data structures, they support this right away. And this big edge becomes, well, the left trunk version and the right trunk version. The other operation to think about this is what happened to this Voronoi vertex. This is a Voronoi vertex in the original diagram, right? By making the original tiles shrink, this Voronoi vertex had valence 3, right? When points are in general position, the valencies are always 3. So what do I do when I shrink all the tiles? I open up this vertex. This vertex is like a seed of valence 3, so therefore it becomes 3 vertices. You see that? This vertex becomes 3 vertices. Actually more, it becomes, it induces a triangle. So where are the additional connectors or edges that are the result of the subdivision step? Well, the new ones, I just draw them dashed. And you see the new types of elements that we need to support. Okay, you see what happened in the local neighborhood? What happened to this tile and its neighbors? And what happened in terms of fixing the hole that I created by making them shrink? So there are these guys, the triangles that I know, right? I introduced these new triangles. And I produced triangles because this Voronoi vertex had valence 3. And I opened up this Voronoi vertex made it 3 vertices. 1, 2, 3. This original Voronoi vertex now has become 3 Voronoi vertices. That's it, pulling it open. And the other thing is this edge. The edges also are double edges, and I pull them away from each other, and I also make them shorter. So this is also a new creature, right? These types of things. The connecting elements from one reduced tile to the neighboring reduced tile. So in terms of the elements that I have to deal with now, after subdivision, after refinement, or after shrinkage, is I still have all the original tiles, smaller, and then I have a bunch of new elements, but they're always triangles or quadrilaterals. Triangle, quadrilateral, triangle, quadrilateral, triangle, quadrilateral. Quadrilateral always because it's one edge that I pull away from itself, introducing the quadrilateral, and triangles only because every Voronoi vertex is valence 3, has valence 3, so therefore triangle. Very nice. So and this was 1/2, 1/2 mask. Now in the limit, we did this, right? In the limit, we made these tiles go to size 0. The length of the intervals started with 1, 50%, 0. Now I do this too. I use a different mask, not 50%, 50%, but I go to the limit right away. What happens in the limit if I make the tiles shrink to area 0? Again, you can have a slider there, right, to the side, and the slider will show the effect, what happens.
So at the end, you get the triangulation?
You get a triangulation, yes. See, if I shrink this further, or if I had used a different ratio for shrinkage, then this tile ultimately would be just a point, right? If I want this tile to go away completely, I shrink it away completely and pull this, what is it, a pentagon, and make it become the point. What does it mean for the triangle? For the triangle means it becomes even bigger. How large can this triangle become in the limit? In the limit, this triangle becomes the triangle that connects this side with that side and this side. Okay? What happens to the quadrilaterals? They also have to go away. They will go away in the limit. Why? Because these edges, this double edge, shrinks down to length 0 in the limit. So these quadrilaterals become edges. Right? The left and the right edge of this quad goes away. This edge becomes longer and gets pulled and becomes a single edge, namely connecting this side to that side. Okay, so in the limit, and limit means shrinking tiles to area 0, then you get this. Only the triangles remain. Right? The point topologically is still a pentagon. Store it 5 times with just the same coordinates, right? And the quadrilaterals are also still there. They just have area 0, right? But your data structure still has them. What is this triangulation?
The Delaunay.
The triangulation, or the complex, in this case a triangulation in general, or more not necessarily triangulation, is the Delaunay complex. So this is this will be the Delaunay complex, the dual del complex, the dual DC, okay, Delaunay complex. So again, people will ask me why do that? What is it good for? The piecewise constant or natural neighbor in turbulent, assigning a constant value, the same constant value to all the points in this tile that have this side as their closest neighbor. This preserves discontinuities. You can use this scheme to preserve these jump areas, right? Many data sets have discontinuities in images. Different colors come together, different objects come together, different materials come together. When you use a tessellation-based approach, you can use, well, nearest neighbor, do that, piecewise constant. Certain other areas, you want to have some kind of gradual change from one value to the other. This, Delaunay, introduces, of course, immediately a linear blend. This value, that value is a triangle. 3 function values is Gaussian shading, is linear blending of colors or linear blending of function values, right? So you could do these types of operations to have a more discontinuous behavior in your data set or a more linearly varying behavior. The other interesting question is, Misha, whether you can iterate this further and go from this limit and now go further. What happens if you think of doing this over and over again? What is the next step when you go beyond this? I said I start with the Voronoi, then I come to the Delaunay triangulation. Is it the limit? Or can you think of a generalization of such thinking that you refine it in some other meaningful way to smoother something, okay? Think about that. Anyway, also, the data structure that you would need in order to show this is, again, a Voronoi vertex has to have the proper valence built into it, right, to allow this, because the vertex becomes a polygon. Also, the edges have to support, well, the behavior of opening the edge up into a quadrilateral, right? So this is multiple uses, and an edge becoming an element, a vertex becoming an element, and the original tile shrinking, but you have to support that. So the intricate question is, as I said here, you can iterate this corner cutting, right? You have the first object, the original cube, you cut the edges away and you get the level 1. You can iterate the process and now cut the corners away from this guy, right? And you can do this over and over until you get something that is a sphere. The question is, what is the generalization or the application of that type of iterative thinking to this operation, so that you can have a refinement scheme for initially Voronoi diagram-based approximation that gets smoother and smoother. It's not really done, okay? There are different thoughts about that, but it's not really done. So if something is intrigued by that, think about that. Okay, I should talk about triangulations a little bit more. Namely about this Delaunay triangulation. No, it's not a definition. I should say the Delaunay triangulation, and now I'm really talking about the triangulation. Delaunay triangulation is a so-called max-min triangulation. What is a max-min triangulation? What triangle is a good triangle? Is this a good triangle? Or is this a good triangle? Which triangle do you like better? You like the left one better. Why? Yeah. You don't like this one? Well, yes, that's the definition of max-min triangulation. So if I have a convex quadrilateral, then I can a convex quadrilateral quad. Think about that, whether I'm talking about a quadrilateral in the plane or whether this could also be a twisted one in space. Convex quadrilateral, I can triangulate it in two ways, right? I can either triangulate it like that, or I can, I should draw it more extremely. I can triangulate it like this, or I can triangulate it option 1, or I can use option 2. There are only two options, right? Like that. So, and the answer is, this is bad, and this is good, right? Because when I look at the minimum angle here might be this guy. The minimum angle here might be the same angle everywhere, right? The angle is 60 degrees everywhere, right? This is the minimum angle, same minimum angle everywhere, right? So this is the min angle, min, and here we have 6 times the same angle, or with 60 degrees. This is more than 60 degrees, so that's why we like this better. In the spirit of maximizing the minimum angle of the 6 angles that we have in the triangulation of a convex quadrilateral. Okay. Can we always triangulate a quadrilateral in two ways? Is it always? Quadrilateral is point 1, 2, 3, 4. You either connect 1 and 3 and 2 and 4, right? Either the split there is connect 1 with 3 or 2 and 4, right? Always two ways, right? Right? Okay. Point 1, point 2, point 3, point 4, right? It's two ways to triangulate. Only really one that you want, right? You only want, there's only, when it's a non-convex, I only talked about convex quadrilateral. Right? This is non-convex. So therefore, there is only one we have to do 2 for. There is no choice. This becomes really ugly when we are talking about quadrilaterals which are in 3 space, and they are not flat to begin with. Anyway, so this is the non-convex situation, right? There's only one possibility that we allow. Otherwise, we would have this one. This connection creates the triangle outside the actual domain, right? I really only want to consider the interior of the ordered, right? This ordered polygon. The interior is this stuff here. Right? All right. So how do you get a Delaunay triangulation? Of course, we know that if I want to get a Delaunay triangulation, I first write a multidimensional half-edge data structure. I implement in one day a multidimensional construction of the Voronoi diagram, and then I introduce this beautiful shrink operation in the spirit of Do-Sabin, and I have a slider on the side which goes to shrink to 0 and produces the Delaunay, right, triangulation. That's how I do it, right? When you're very brave, you do it that way. But there's a very elegant and simple way to do this based on just this operation or this definition of a max-min triangulation of a quadrilateral that goes back to a mathematician who has worked for many, many decades at the Jet Propulsion Laboratory in Pasadena. And in fact, I chatted with him about the scheme. But that was about 30 years ago. So there is Lawson's algorithm. Lawson's algorithm. Apply use this max-min angle criterion, max-min angle criterion to iteratively, to generate a Delaunay triangulation iteratively. Generate a del triangulation iteratively. Okay. On the left, I want to do an example, and on the right, I will spell out on a high level the steps that are necessary. On the highest level, it works like this. The assumption is that at an intermediate state, I have a Delaunay triangulation, and then I will insert the next point in such a way that I will not violate the Delaunay criterion. And the triangulation is Delaunay if it is a max-min triangulation, or and vice versa. Every max-min angle triangulation is a Delaunay triangulation. Okay, it's just another way to define Delaunay behavior. So again, if I have a triangulation which is a max-min or Delaunay triangulation, and I insert the next point, then I want to make sure that after the insertion, the new triangulation is still a max-min or Delaunay triangulation. And I want to enforce it by using this decider. Okay, this decider always looks at quadrilateral configurations and makes sure that for the quads I use the best possible triangulation. Okay. So there is this issue of starting, right? How do I start? Again, it's for scattered data. I'm given 1,000 sites. How do I start? In the plane, I start with a bounding triangle. Okay, I just start with one bounding triangle, which for sure is a Delaunay triangulation, right? A big, fat, happy triangle that contains all the other sides. Huh? And then I will take the sides and insert them into the bounding triangle, and just during the insertion, I make sure that all the new stuff will also be good, right? Good in the max-min criterion. So this is how I start. Helper points, right? I make these maybe as asterisks, so I have a bounding triangulation like this. Okay. So one, use a helper triangle that contains all given sides. Okay, and then I will pick the first side, the first real side. 2, pick sides one by one, and insert them into the current Delaunay triangulation, ensuring the max-min angle property after insertion, ensuring max-min angle condition after insertion. Is this algorithm faster or better than doing it via the Voronoi diagram step first? Yes, it is. Okay, so there are many ways to construct the Delaunay triangulation. Anyway, so I take the first point, right? Okay, so this is the first original side. So if I insert the first original side, then what's the triangulation? that I get after insertion? It's only one way, right? It is, follow your intuition. It is this triangulation, namely connecting this first of all the real sides in there. Okay, good. And then you move on. Now I have to talk about next steps once you're a little bit further in, and when you go from, say, a triangulation consisting of 1,000 points to 1,001 points. After many insertions, you have, for example, this situation. Let's say you have this situation. The most beautiful of triangulations, right? That's the only one I can draw anyway. Okay, so this is the current triangulation. You have to insert the next point. Inserting the next point maybe is this one. Okay, this is the next point that I insert. Okay, what do I do initially? This is the way the algorithm works. I just tell you. I find out that the next side to be inserted lies in this triangle. Therefore, the way I retriangulate is connecting this new inserted point to the vertices of the triangle that it resides in. Okay? So the first step is doing this. And now I have to go back to go back to the definition of max-min angle, and I have to analyze what I just did. Okay, is now the triangulation good in the max-min sense? Is it or is it not? Can I improve it? The atomic step of the Lawson algorithm looks at quadrilaterals, right, and tries to improve the situation for quadrilaterals. So the stencil of convex quadrilaterals that gets affected by this insertion and by this retriangulation is this stencil. Okay. This is the region that gets affected by the retriangulation the way I've done it so far. Okay? Okay. So, for example, here's one quadrilateral that is convex, right? You see this quadrilateral? This is a convex quadrilateral. And I've triangulated this in a certain way. And I can improve. Actually, quadrilateral I have to look at is this one. Okay, sorry, don't want to confuse you. So these are the quadrilaterals that we have to look at. These are not the fat lines. These are the fat lines, okay? And the original edges are thin edges, just from memory, from context. Okay. So these were there. And what I have drawn is I've outlined or highlighted 3 convex quadrilaterals in the neighborhood, right? There's this one convex quadrilateral now, this one, and this one. And Lawson says, well, is this a good way to triangulate this quadrilateral? Is this a good way to triangulate this quadrilateral? And I have a third quadrilateral here. Which one do I have to improve? Here, right? Here you have this ugly, skinny triangle. It has to go away. It has this horrible angle there. And indeed, I can improve that by removing this edge, the old edge, and flipping it. Okay? And say, I would not improve the situation if I were to flip this edge. If I were to flip the edge, this is edge flipping. It's also called edge flipping, this operation. I flip this edge to this one. It doesn't improve it, just by inspection. If I take this one and flip it to this one, it will not improve it, because if I were to flip it to this angle here probably is too small, right? So this is fine. These are 2 nice fat triangles. These are okay, and now these are okay. So first step is you take a triangle, insertion point, and you connect like that, right? Insertion point. Okay. Take point, put in triangle, connect point to edges of triangle, to corners of triangle. And second is edge flipping, flipping edges of the quadrilaterals in this neighborhood. Okay? Edge flipping. It's called edge flipping. Edge flip. Edge flipping. And it's question mark. Sometimes you do, sometimes you don't flip. And so the issue there is, you look at this, and here's a new point. And this guy will have neighbors there, neighbors here, and a neighbor here, right? So this is the original neighbor triangle configuration. So you have one quadrilateral here, quadrilateral 1. You have one quadrilateral here, quadrilateral 2, and you have another one here, quadrilateral 3, right? And you have to ask the question, which quadrilateral should be inside which, in which quadrilateral, in which quad QI must I flip the diagonal? Must I flip edge flipping? Flip the diagonal, the edge. Right? Do I have to flip this to make this, or take this away and make that? So you do this. It's a big loop, right? For all given points, do insert point, and then always ensure when inserting that I maximize the minimum angle. Boom. Okay. But there's something ugly to this, and then I will stop. But when I do these flips in these quadrilaterals in this local region, then what will happen? It can potentially have a global effect on edge flipping. It's not restricted. Okay, this so beautiful this operation that looks so beautiful and seems so local ultimately might have an effect like a growing fire. No? That this flipping is not just restricted here, but because I flipped here, all of a sudden I have to consider something here. I've introduced new convex quadrilaterals, right? I have a new convex quadrilateral now by taking this edge away, and inserting this edge. I have another quadrilateral that I have to look at. This one, for example, right? This is a quadrilateral here that I have to check. Is this the right diagonal for it or the other one? No? So whenever I do these edge flips, they have an effect on a neighborhood, and that neighborhood has an effect on the neighborhood of the neighborhood, and so forth. So in the worst possible case, this edge flipping, they do not terminate before they have touched everything. So, but edge flips can or are have in general a global effect. Have a global effect. Okay, and again, there's an in-depth analysis of the algorithm and the statistical nature of this beast in the papers by Lawson, where he talks about the expected time behavior and so forth. Okay, and then the average expected time is still very, very good. Beats many other methods. That's it for tonight. Let's see. Any last question about Project 3? No? Okay. I see a few more demos tonight, like 3 or 4 demos, so please stay and show me. And that's it for tonight. Thank you. Bye-bye.